All right, everyone, good morning. We will go ahead and get started since it is 9 o'clock. Thank you so much for joining us today for the National Biodiversity Teach-In Earth Echoes Oceans Day. We're really excited to have everyone here with us. And we're really excited to have Alan kick it off for us. Alan Lewitus is a branch chief at NOAA's National Ocean Service Center, where he oversees the planning and management of competitive research programs addressing such topics as hypoxia, harmful algal blooms, and sea level rise. His background is in phytoplankton, ecology, and physiology, with research interests that include coastal eutrophication, the ecology of harmful algal blooms, and microbial food web dynamics. Prior to joining NOAA, Dr. Lewitus spent many years in academia and then in state government, where he was involved with marine resource management. He holds a BA from Rutgers University and an MS degree in marine sciences from Moss Landing Marine Laboratories with a Physical Oceanography discipline, and a PhD in Biological Oceanography from the MIT Woods Hole Oceanographic Institute joint program. Since joining NOAA in October 2005, Dr. Lewitus has been closely involved in activities related to research and management of the Gulf of Mexico ecosystem, including coordinating and facilitating efforts to mitigate the Northern Gulf Hypoxic Zone, aka the Dead Zone. And he will be sharing some of those experiences with you today. We are really excited to have him here at Earth Echo. We have a whole unit on dead zones. We focused on the Chesapeake Bay, but some of the issues that plague the Gulf are similar in a much larger scale. So, Alan, I'm going to give it to you to take it away.
Very good. Thank you, Allie. Can everybody hear me okay? Okay. All right. I'm going to talk about a very challenging environmental issue, the dead zone in the Gulf of Mexico. Dead zones, whose scientific term is hypoxic zones, are large areas of water where oxygen becomes so scarce that animals either flee, or if they can, they do flee, but otherwise they'll suffocate. What I'm showing here is a visualization of the dead zone shown down here, and along with the huge watershed. All this area here drains into the dead zone through the Mississippi River. And as I'll explain, the nutrients that are produced in the watershed and are carried down the Mississippi are the cause of the dead zone. And I'll talk about that later. So you can imagine, to try to reduce the nutrient loading that is going down into the Gulf through this huge watershed area is a big challenge. You have to have a very large multi-state collaborative effort, very cooperative effort to reduce the large amounts of nutrient pollutants that are entering the Gulf of Mexico dead zone. I'll talk about the way federal and state governments and other institutions are collaborating on this effort and trying to get it done, trying to shrink the dead zone. Let's see. So here's my outline. I'm going to talk about the dead zones and in general, talk about hypoxia issues. Then I'll talk about the causes of dead zones in general, including their ecological impacts. And then I'll focus a lot on the Gulf of Mexico dead zone, including the interagency Hypoxia Task Force, which is charged with managing the dead zone and reducing it. I'll talk to you about the activities that they're undergoing. And then I'll give you a little bit of touch about the types of research that are involved right now in trying to guide the Hypoxia Task Force and provide the scientific information to allow them to do the best job they can in terms of managing the dead zone. Talk about monitoring, and then I'll talk about all important models that help manage a dead zone. And I'll end with just some general thoughts about where our progress is right now with watershed nutrient reduction, sort of leave you with some kind of idea as to where the future might be going with this issue. By the way, you can interrupt me with questions anytime. Just yell or give your questions to Allie, whatever
Does
works.
that come in through the chat box?
So
Any
first,
questions that come in through the chat box, I'll interject with, and we're taking some on Twitter as well, so I'll let you know as soon as they come in.
Great, thanks. Okay, so what are dead zones? This shows some general responses of organisms, including fish, to low levels of oxygen. So as oxygen gets lower and lower, you see there's different types of impacts on different organisms. Generally, scientists use 2 milligrams per liter as the cutoff point. That is, below that level, we call the waters hypoxic. And that's what a hypoxic zone is, waters that are below 2 milligrams per liter, generally. Some use different cutoffs, but 2 makes a lot of sense and is pretty common because the detrimental effects to organisms are pretty plentiful below that line, not so much above it. So so that's the definition of that. The other thing to keep in mind is that hypoxic zones, we know about impacts to a great extent because some are very obvious, and mostly fish kills. When a dead zone triggers a fish kill, it's pretty evident. But most of the harmful impacts of hypoxia or dead zones does not occur at that level. You don't see in many dead zones many frequent fish kills, though they do occur. Most of the impacts are called sublethal. They're harmful effects on the health of organisms, on the food source of organisms, things that are not directly obvious but have great repercussions in terms of the health of the ecosystem overall. So some of these sublethal effects can be carried over into the reproductive performance or the growth potential of organisms. So there's a lot of effects beyond killing fish. You need very sophisticated scientific tools to sort of determine some of these effects, including food web models and use of bioindicators and other types of tools. So it's not all that straightforward sometimes. Why do dead zones form? Well, I should preface this by saying some dead zones occur that are not do not occur because of the influence of nutrient loading. Some are offshore. They occur offshore, and they're really caused by upwelled waters and low oxygen water being brought up to the surface. But what I'm going to focus on are those that are more, and these are the more common ones. Those that are caused by excess nutrient loading. We call eutrophication. And what happens is nutrients, primarily nitrogen and phosphorus from land sources, are loaded into coastal waters. And nutrients are an essential element for algae to support the food web. However, in excess, they can be harmful. There can be an over-enrichment of nutrients. And when that happens, you get an overgrowth of phytoplankton. Blooms occur. And from those blooms, they eventually stop growing. They dissipate and sink to the bottom. And that's where they're worked on by bacteria. Bacteria decompose the phytoplankton, the algae. As they do that, they consume the water, oxygen out of the water, and they can produce a dead zone. And that's shown by this dead crab. That's a dead zone right there.
Alan, sorry, we have a question that came in on Twitter, and it's just asking, those excess nutrients, where are those typically coming from? Are those natural causes, man-made causes? What are you typically seeing those come from?
Good question. Leads right to my next slide.
Timing.
There are lots of sources of nutrient pollution, and I didn't ask that question ahead of time, really. But anyway, there are numerous sources, and actually different dead zones are caused by different potential sources. One of the more common ones is agriculture, and primarily through fertilizer application. So fertilizer are rich in nitrogen, phosphorus, and the amounts that are not taken up by crops are left over, if you will, and then they can load into the rivers, and then they're carried down to the estuaries. So that's one source. Wastewater, sewage. Sewage treatment plants have waste that's highly rich in nitrogen, often phosphorus as well. Stormwater runoff is another source where if you don't have a good facility to sort of buffer the nutrients, they can be drained right into estuaries and coastal waters. And then there's industry, puts off nitrogen, phosphorus, particularly nitrogen, and that could be through air pollution as well as groundwater. And so that atmosphere covers that part. So there's various sources, and different dead zones are influenced in different ways by these. The Gulf of Mexico dead zone is primarily influenced by agricultural sources, fertilizer use, the heavy farmland and farming activities in the Midwest is a big source. On the other hand, in Narragansett Bay, which has another seasonal dead zone, sewage effluent or wastewater treatment effluent is the major source of hypoxia there. So this is just to show you how big a problem it is and how much it's growing. Dead zones really started taking off around the 60s and 70s. And before that, there were not all that many that were reported. During the 60s and 70s, the reason they took off was related to eutrophication, excess nutrient enrichment, which and this is really globally, and it sort of exploded in that time, the 60s and 70s, and that's reflected in part by an increase in the amount of not only hypoxic events, but harmful algal blooms. And this explosion was traced to an increase in man-made nitrogen production primarily, most of which came from fertilizer from agriculture use. So the increasing input of nutrients to coastal areas over the last 50 years really has resulted in what people might call system overload. It's really led to a lot of eutrophication-linked problems. And there's a strong correlation over this period between population growth, increased nutrient discharges, increased algal production, harmful algal blooms being an example, and increased occurrence of hypoxia. Now, coastal surveys of the United States and Europe have found a staggering 78% of the continental U.S. coastal area and approximately 65% of Europe's Atlantic coast exhibit symptoms of eutrophication. So, bottom line, the increase in hypoxia reports is related to this increased nutrient loading. And I have another slide that sort of emphasizes that similar thing. This is from an interactive map on the World Resources Institute website.
With these global dead zones, and as you talked about the Gulf of Mexico dead zone exploding, one school, Heritage, asked, what is the size of the Gulf of Mexico hypoxic zone? So if you had to compare it to something, what would that size be just for comparison purposes?
Oh, he's stealing my thunder again, but yeah, that's coming up. But I will say that the dead zone in the Gulf of Mexico is the second largest in the world, and when it's at its higher end, it's the equivalent to the size of New Jersey, area of New Jersey. When it's very low in certain anomalous years, it'll be somewhat smaller than the size of Delaware. That sort of gives you a handle of the range. In terms of numbers, the record, I believe, is on the order of 23,000 square kilometers, which is, a little bit, I think, a little bigger than New Jersey. That's when you start approaching Massachusetts. But that's the highest. But we've come very close to that on a number of occasions. So that's not an extremely high number. New Jersey, the state of New Jersey, is about the average size we get in these days. Does that help?
That's a perfect comparison and representation.
So this is actually a pretty good website if people are interested. I have the email, what do you call it, the URL there. It's an interactive map, allows you to see what areas are known as eutrophic and which are hypoxic, and it has other aspects to it. So there are 476 sites with documented hypoxia in the world at the last count, and over 300 in the U.S. And as I showed before, the number of water bodies with documented hypoxia has increased by about an order of magnitude during the last 50 years, from less than 50 in 1962 to 400 in 2008 and 476 today. And in the U.S., in 1960, 12 hypoxic zones were documented. Now there's over 300. More than half of examined estuaries in the U.S. Are hypoxic at one point in time. So that's pretty daunting. Okay. Well, now I'm going to talk a little more about impacts of hypoxia, and focusing mostly on the Gulf of Mexico, though I think all these things I'm going to say it can be applied to other regions. So the Gulf. This is the Gulf of Mexico coastal area, and the Mississippi River flows down here as well as down here. And this is actually before the hypoxic zone was a regular occurrence in 1961 to 65, just showing the fish catch hotspots. So the darker colors are where fishers went out and caught most of their fish and shrimp. And whoops. So that sort of circles that area to make the point. So this is the optimal, this is where the fish and shrimp hung out. This is their optimal habitat. The temperature, salinity, food sources, everything was pretty optimal, and that's why the fishers went there. That's the same area as today occurs the dead zone. So right now, every time the dead zone occurs, it is devoid of those fish and shrimp. And that tells you something. It makes sense because that's a very productive area in the past, and now the production by algae is working against it, creating the dead zone. But the other thing to get out of this is that one of the impacts of the dead zone of the Gulf of Mexico is to sort of chase fish and shrimp, because they can move, away from this optimal area and into outer areas that are less optimal in terms of their favored temperature, food sources, those sorts of things. And that has a cost. There's been some studies that show that the health of fish and shrimp, the as indicated by some markers, biomarkers that you use, is lower as a result. And some recent evidence suggests that the average size of shrimp might be affected by the recurrence of hypoxia. So that's very important for the commercial fisheries, the average size of shrimp. So there's more to be done on that, but there is a habitat loss that occurs with the Gulf of Mexico hypoxic zone and other hypoxic zones as well. Now, here are some documented impacts of the hypoxia in general. The list is not complete, but these are some of the major ones. I'll just talk a little bit about the Gulf of Mexico shrimp industry because they're one of the ones that are very much affected, as I showed you previously. Shrimp is the largest U.S. commercial fishery. Texas and Louisiana lead all states in catches, and those are the coasts that the hypoxic zone affects the most. In 2004, Texas and Louisiana landed 64% of the nation's shrimp tails. So shrimp is the main cash crop of the Gulf. In 2006, it generated nearly $400 million. So the idea is that continued expansion of hypoxia may have important economic consequences by reducing the number and potentially size of shrimp if it keeps going. Another thing that has been recognized in areas where there is a big and recurring hypoxic zone and it's getting worse is a thing called tipping point. And this is from, it'll just be described in this passage. This is from a 2008 EPA Science Advisory Board expert panel that concluded the following. The panel finds that the Gulf of Mexico ecosystem appears to have gone through a regime change with hypoxia such that today the system is more sensitive to inputs of nutrients than in the past, with nutrient inputs inducing a larger response in hypoxia as shown for other coastal systems such as Chesapeake Bay and the Danish coastal waters. Changes in benthic and fish communities with the change in frequency of hypoxia are cause for concern. The recovery of hypoxic ecosystems may occur only after long time periods or with further reductions in nutrient inputs. If actions to control hypoxia are not taken, further ecosystem impacts could occur within the Gulf, as has been observed in other ecosystems. So the tipping point being, whether hypoxia gets so bad for so long that we reach a point where it's very hard to restore the system back to how it was previously. We're grappling with that. Are we in a tipping point? Have we shifted the regime? I think some would say yes. Can we restore it? I think that's still a possibility. According to models, they appear to indicate that that is possible, and that's why we are going down the road of trying to fix it. So just one last thing about impacts, because this is very fascinating for one thing, but also very troublesome. And that's recent studies have shown that low oxygen waters can have harmful effects on fish health. Talked about some of that before. But the thing is, they can affect health under even moderate conditions. In other words, not quite hypoxic, maybe hypoxia was 2 milligrams per liter, maybe even up to 3 or 4 milligrams per liter, you still see these effects. And you still see them when fish are, intermittently exposed to hypoxia. So it doesn't mean that they have to be immersed in it for a long period of time. They can encounter it, back out of it, encounter it, and that still gives that stress effect. And this shows some examples of croaker, Atlantic croaker, that were caught in hypoxic zone and normal oxygen zones, showing the effect on the gonads. much much impaired in the hypoxic zones, and this, of course, has repercussions for the performance of the fish in terms of reproduction and the growth potential and all that. So it's a major issue, and so again, going back to what I said before, fish kills are certainly an obvious effect, but sometimes it's these things you don't notice unless you really dig into it that are also occurring, and how that translates into, you know, the population health or the ability to propagate these populations, as well as the ecosystem health, is a whole very important other question. Okay, I could stop. Any questions that I could field right now before going to the next?
We have a few. I didn't want to cut in and steal your thunder, but a couple. So we have Mrs. W's class is asking, is the dead zone predicted to grow in the next few years, and if so, by how much?
That's a great question. Or is that
something that's difficult to predict?
Well, as I'll get into and actually touched upon, it really comes down to, I mean, there's many factors that contribute to dead zone. Let me be clear about that. But the one that's sort of, overriding, if you will, and certainly the one that we can do something about, is nutrient loading. So it really, our prediction is that the dead zone will grow or shrink with how we do with nutrient loading, whether we increase nutrient loading or preferably decrease it. And what I'm going to talk about are all these activities that are, I'm not going to get into detail on the activities. I'm going to tell you that there are a number of activities that managers around the country are implementing to try to reduce nutrient loading. So my thought is that the dead zone will decrease in the future, only because of the hope, but more than hope, the expectation and anticipation that we're going to get our act together and actually reduce nutrient pollution into the Gulf. And I'll show you, I'll end with, I'll continue with some of this doom and gloom, and then I'll end on the up note as to where I think things are going to improve. Anything else?
There's a lot of questions coming in about what can we do to improve the dead zone, so we can go through those as you kind of get to that part in your presentation. Okay. But there's a lot of questions coming in about what classes can do.
Okay. I'll probably have a good place to talk about that. Okay, so now it's going to sort of focus on the Gulf of Mexico dead zone and go into some of its characteristics and history and that sort of thing. So this shows you the watershed. I showed this before. This watershed drains the Mississippi River Basin, drains 40% of the contiguous U.S., which is the connected U.S. Most of the nutrient load to the Gulf comes from Midwest agricultural regions. So these darker regions up here are pretty high sources. The Corn Belt, Iowa, Illinois has major production of corn that is contributing to it. Talk a little bit about that. As I said before, the Gulf Dead Zone is the second largest in the world, and is the largest in the U.S. The major source of nutrients to the dead zone is from agriculture, and corn and soybean fields represent 52% of the nitrogen and 25% of the phosphorus that goes to the Gulf. Corn. The thing about corn is it's very inefficient about taking up nitrogen. So when you apply fertilizer, which is rich in nitrogen, Corn doesn't take up a high, as high a percentage of it as some other major crops do. So it therefore leaks a lot. It'll take up some fraction, but the other, it leaks out of the system, and that's the stuff that gets drained into the Mississippi River. So just, it's just an unfortunate thing that corn is not the kind of green crop, if you will, that would be nice to have. But it's certainly very important for food as well as ethanol and that sort of thing. It's just that we have to do a better, more effective job of applying fertilizer and implementing different practices that try to capture that nitrogen before it leaks into the waterway. Also, substituting corn and is another thing. Especially, I don't want to go too far in this area, but corn's being used for ethanol and biodiesel, but there are other alternatives for that. So alternative energy sources are a thing that might come into play as well on the nutrient pollution issue, getting away from corn. But and there are movements towards that. But I don't want to get into the politics in this talk. Now, so that's the watershed, and here's the Gulf of Mexico dead zone. So this, here's the coast. Here's the Mississippi that comes down here. It splits off into the Atchafalaya River, which goes out west and fuels this part of the zone, and together they form the dead zone. The dead zone can vary in any given year in terms of its size. This shows two. I should mention how it forms or when it forms. Most of the nutrients that fuel the dead zone come down in the spring. So the dead zone starts forming in the spring in response to nutrient loading, but it doesn't peak until midsummer when the nutrients are transformed and all the cycling of nitrogen occurs and oxygen consumption occurs. So the midsummer is when.
And so that was one of the questions, Alan, is sort of at what rate do dead zones form? Does it vary depending on nutrient amounts, that sort of thing?
Yeah, that's a good question. The rate doesn't vary by the nutrient amount unless, well, it does if the duration of nutrient loading is extensive, then you'll have a probably more opportunity to process the nutrients in a longer dead zone. I mean, longer lived dead zone. But the transformations that occur, you have to have the bloom form, the sinking of the material, the degradation, and then there's some cycling that occurs in exchange with sediments. So there's a lot of processing of the nitrogen through different nitrogen forms often until you support enough bacteria that can deplete oxygen to the level that you need to bring it down to hypoxic or anoxic conditions. The other factor I haven't mentioned at all, but it's a critical factor, is stratification. Stratification is when you have different density layers on top of each other that prevent mixing of the water. And that's critical because what happens is the bloom occurs and it sinks. And the bottom waters where all the bacterial activity occurs in the water column, but most of it ends up in the bottom. And that's where the hypoxia water is. And if you have free exchange with the surface, that's oxygen that's being mixed in with the dead zone water, which would break it up. So when you have stratification, when you have, in essence, a lens of different density water, lower density water, then you have a barrier to that exchange with oxygen. So that when you have high stratification, that's another factor that contributes to hypoxia. And if that lasts a long time, you'll have a longer hypoxic zone because you'll have restricted mixing. So a lot of factors, but those are the two things: the amount of nutrients and the cycling, and then the stratification, and then the hypoxic zone lasts for a long, long time throughout the year. Goes from early spring to late fall. So it's not just a short-lived event, though it can be broken up by weather events. A hurricane moving through a dead zone is good from the dead zone aspect. It breaks it up. It's not good from other aspects. So it's not a solid blob. It varies in time and space, and also gets broken up and then realigns itself, and it's very dynamic. So the point on this, I just show these two comparisons because one on top in 2011 was a big dead zone year, and that's because that was a year that had very high rainfall. It was a flood year in the Midwest, and when you have a flood year, you have more greater amounts of nutrients being loaded down in Mississippi into the Gulf. And so in that year, we had a dead zone of the order of 22,000 square kilometers, I believe. Anyway, this is one of these that we call the size of New Jersey. And then in 2012, we had a drought year where there was much less nutrient loading into the Gulf, and that affected the dead zone in the other way. And that was on the order of 7,000 square kilometers. So it can vary year to year, but more and more often we're having these large dead zones in recent years. Okay, so this is talking about this interagency task force that is charged with trying to fix the dead zone. In 1998, Congress, they recognized the extent of the problem, recognizing that nutrient loading was linked to the dead zone, and recognizing that nutrient loading was linked to the dead zone, and that it was getting worse and worse each year. And so they passed legislation that led to the formation of the Hypoxia Task Force. And the task force is an interagency, cooperative, collaborative, that today includes 5 federal agencies, 12 state agencies, and tribes within the Mississippi River Basin. So in 2001 was the first action plan from the task force, and the action plan is called Action Plan for Reducing, Mitigating, and Controlling Hypoxia in the Northern Gulf of Mexico. And it had a goal, a very important goal, and it's sort of some of it's shown here, to reduce the 5-year running average of the hypoxic zone area extent to less than 5,000 square kilometers. And I'll show you a graph of how that sits compared to what it is now. And the thing that they focused on was achieving that goal by reducing the discharge of nitrogen into the Gulf. That was in the original action plan. And then in 2008, there was a revised plan that actually recognized at that point that phosphorus also was important, and really you had to reduce both of those to give you the best chance of reducing hypoxia. So that goal really has driven everything that the task force does, and it's all spelled out in the action plan with various actions that are different ways to get at that goal of reducing nutrients and reducing hypoxia. Now, this does show the trend in the size of the hypoxic zone. This is a long-term data set taken since 1985, I guess that is. And here's the goal of the action plan. This is 5,000 square kilometer. These bars are the aerial extent, the size of the dead zone in subsequent each year. And this is the goal, 5,000. These are the actual measurements, these bars. That's pretty depressing. So it actually did increase from the 80s to the 90s, and then it sort of has plateaued and remained fairly high most of the time. In some cases, we have it like this is a drought year and so forth. But it has remained roughly 3 times the size of the goal. And the goal, I should say, was established because it reflects the potential size of the zone based on modeling hindcast that existed before the large fertilizer use and large increase in nutrient loading. So it's sort of, that's a way to restore it back to better times. But we're not close yet. So, so there's still a major effort to be had, and building upon what's already been done in terms of reducing nutrients to get to the reduced hypoxia. So now I'm going to talk about the scientific research that is used to inform the Hypoxia Task Force of the characteristics of the dead zone and the factors that control its properties, and these are critical for giving the task force guidance on how to manage, how to make, given the best chance of meeting the goal to reduce hypoxia. Any questions?
I have a few. Again, a lot of them are about sort of fixing it. One interesting question is, are there any fish or animals that can survive in this type of area, or that would be able to actually help break down some of the algae and lessen the dead zone?
That's a good question. There are some hypoxic tolerant organisms, not so many fish or larger predators, and even smaller ones like zooplankton, the copepods. They're also susceptible to low oxygen. So there's not a lot of not a lot of organisms in the dead zone that would eat the algae, but actually that's not so much of a problem once you have a dead zone. I guess what you're talking about is eating the algae before they degrade and then form the dead zone. Well, there's lots of organisms that do that anyway, but when you have an overgrowth of algae, when you have a bloom, it saturates the system. So, it's not in balance anymore. So the predators, the zooplankton, for instance, can't keep up with the high level of production in biomass that the bloom is producing. So it's a good question. It's just not, that's part of the problem is they're saturating the prey potential. So they're saturating their predators' food consumption, if you will. So leaves a lot left over. What was the other part of the question?
That covered most of it. It was about, if animals can survive and that sort of thing. And then, yeah, so, and then we have about 7 more minutes left before the end of this webinar, just to give you a time check.
I'll zoom through it. I did want to mention, yes, some of the fauna, some of the sessile fauna, the fauna that, worms and things that are sessile on the bottom, there are some that survive, but very few. And the diversity is really very, very low, and they're not good food sources, but there are some that survive. Okay, let me get through this. Now we're talking about monitoring the dead zone. That's so critical because, for one thing, we want to know what characteristics are involved or how it's characterized, but also we want to know what progress the management actions are having. So if you're trying to reduce nutrients and reduce hypoxia, you got to have a handle on what the hypoxic characteristics are. So monitoring is important. There are 3 ways that we monitor down there. Each has its advantages. Ship surveys are very important. They give you the ability to sample a number of sites, and typically you have hydrocasts that measure various properties at several sites. They're expensive, ships are, and we don't go out all that much, 1 to 3 times a year, so you don't get a lot of temporal coverage, even though you get good spatial coverage. So other types that do some of that are observing systems and gliders. I'll talk about those. The ship surveys, just to show how extensive the survey goes, this is quite a bit of sampling, on the order of 100 sites. They do transects. So you do have good spatial coverage on a one-shot deal. The other thing to mention here is these dots right here, the colored dots, are observing systems that are positioned in various strategic places along the dead zone. And observing systems, there's different types, but this just shows one of them, the ones that has a moored platform that different instruments are hung off of, and at different depths collect oxygen, conductivity, temperature, etc. So this is good because they collect continuous data, 24-hour if you want, and so it's great temporal detail, but they're only in one site, only one spot, so you'd have to have a lot of these to have any kind of spatial coverage. So it's a good complement, ships and observing systems, but what's come along fairly recent, they're now pretty routinely used, are gliders. These autonomous underwater vehicles, or robotic technology, and these can cover both large areas as well as high frequency. So you can get a lot of data from a lot of different areas. So this is something we're really pushing toward right now. It's a challenge in the Gulf because of the Gulf of Mexico is a pretty high density gradient, and especially challenging when you're trying to control the buoyancy of these gliders in shallow waters. But we're getting the kinks out, and I think we'll be ready for very widespread application of these things for monitoring the dead zone, which is going to really add to our information. Modeling is critical for managers. We are investing in several models, several different types of models to look at the dead zone. They're critical to understanding the factors that control hypoxia and the reasons you have large zones versus small zones. And this is in turn critical for managers to come out with effective strategies to reduce hypoxia. So the models give you predictions. If you do this, then you're going to have this much success. If you reduce this much nutrients, you'll reduce the hypoxic zone by X amount, these sorts of things. Several types of models are being used. We develop them to assess both the hypoxic zone dynamics and to understand all the physical and chemical, biological, geological, all those processes that influence the hypoxic zone. We also use them to predict the size of hypoxia under different nutrient loading scenarios and management strategies, so sort of already said that. So these are two of the types of models. We're investing in many others besides those. We also have a forecast. We use these models to generate a dead zone forecast every year, like a hurricane forecast, but our forecasts tells the public and managers how big or how small the dead zone is expected to be in any given year. Okay, just real brief, I'm going to kind of skip over this just to say that modeling dead zone impacts is another way to model, and this is very, very complicated. You have to incorporate all these factors on the dead zone impacts. I talked about the reproductive issues, put all that into some type of model that tells about organism performance, combine that with the environmental factors or conditions, and that gives you ways to predict what the effect the hypoxic zone will have on different fish populations in the future. This is where we're going. We're still advancing, and this is a really important area of research. All right, watershed nutrient reduction, talk a little bit about what's being done, and a little less about doom and gloom, more about what is really being done in a very strong, serious way. And that is that we have a very strong cooperative effort right now between states and federal agencies that are really bearing down on trying to reduce nutrients from the watersheds where they're the most problem. There's a congressional requirement for a annual progress report now, which was done to make sure that the advances that have occurred will continue. And there have been some very good advances, one of which is the states that are in the Mississippi River Basin have come out with their own state strategies. And, they put a lot of effort into these. So this shows Minnesota, where they're intending on reducing nitrogen by 20% and phosphorus by 35% by the year 2025. And every state has these sorts of goals, and the idea is that together they'll all sort of have sort of, if you will, synergistic effect in reducing nutrients down the Mississippi. So there is some hope that that's going to have an effect. I should say that there are some successes. There are some tributaries feeding into the Mississippi where nutrient reductions have occurred through these efforts. So there are examples. And I also should say that there's a lot of investment by the funding agencies. USDA has really come forward with a lot of money to incentivize farmers, landowners, and agriculture industries to reduce nutrients with various incentives. So those are taking place. And this is my last slide, and it's complicated, but I want to make a couple of points. This shows right here, this is USGS information on nutrient loading, and the details aren't important, but it's just basically there's no real change. It's steady. This is nutrient loading into the Gulf, the net nutrient loading over time. Hasn't really changed, right? But they look more closely at the data, and you can't see this very well, but bottom line on this is that they divided it into high flow, high stream flow, and low stream flow. And they found a difference. The high flow is decreasing over time, the low flow increasing. And so it seems like the nutrient loading reductions have an effect on the high flow. And that's the stuff that comes down that is not stored in the sediments. It sort of just comes down the river. And that's the stuff that would be affected more readily by nutrient reduction management actions. And that is decreasing. It's the low flow, which is really the groundwater input, which is increasing and making the net loading net zero, no change. And the hope is over time that both of these will decrease, that there's just basically a lag on the groundwater before the groundwater starts feeling the nutrient reduction actions, and that the groundwater starts becoming less nutrient rich at some point. What that point is, we'll have to go to the models, but that gives me hope that there is going to be a turning point at some point. So, and it could be pretty soon. So I leave you with that. That's a hopeful thing. The signs are that we are going to make progress, and we're certainly trying very hard to do so. Okay, I'm done. Mm-hmm. Well, in the beginning, it was a real concern that there was some exacerbative effect, so that the two, like the oil spill, would add more stress on top of what the stress was occurring in the dead zone, and vice versa. They would both act in concert to add more stress to organisms. But the spill didn't really it certainly occurred far away from the dead zone, but even the distribution of the oil, yes, it encroached on it a little bit, but it was not all that major a factor, just by circumstance of being pretty distant away and the way the circulation worked. So that's my understanding, is that I know there's some research to nail that down more, because we're really not yeah, unprecedented. We're still learning. Let's put it that way. Good question. I think one of the ways is that the bacteria run out of fuel, so they consume some of that cycle and continues, but there is a point where the fuel, the food source to them, runs out. But the other thing that goes on is that the mixing breaks up and when the waters start getting more rough and the currents shift, the mixing can break up the zone, and those two factors combined lead to its dissipation. Even in a calm water, you can't go on forever without a continued fuel source. There are. I will tell you that there is that science hasn't advanced as much as we'd like. There are some studies on that. Um, the problem is what I mentioned before. You can document and quantify costs from fish kills due to hypoxia, and that's done all the time. But you're not getting at maybe the major impact, which is these, quote, sublethal effects that you'd really have to tease out with models to see what those costs are. When I showed those long-term predictions of populations, if you have a 20% reduction in population, say 50 years from now, that's a cost too that's hard to figure in.
So yeah, and I know the Chesapeake Bay Foundation, attempts to do that as well and factor in recreation and tourism, and there just seem to be so many factors involved.
There are, and when that sort of reflects a real need right now is to have a better integration between the social and economic sciences and the life sciences, because we grapple with that all the time. And harmful algal blooms, we try to come out with estimates all the time, but really need to have a very tight interdisciplinary based study to get at those questions. All right. Well, we do have to wrap up and begin our next webinar, but Alan, I wanted to say thank you so much to everyone that's here and that's registered.
We will be sending out a follow-up email with some resources at earthecho.org. You can check out the resources that we have there. We have lots of action guides on how to get out and take some action in your own community, whether it's installing a rain barrel to help with stormwater runoff or planting a riparian buffer. There are lots of ways that you can help with lessening dead zones in your own area. So thank you again so much, and everybody have a great rest of your Friday.
Thank you.
Thank you.